Welcome to the second fundamental theorem of calculus. Here is the theorem. So go ahead and make sure you get this written down. And then we will do a quick example to sort of prove what this means. We'll start with this example right here. We do have things in terms of t here, f of t dt, as the integrand, because we do not want to confuse it with the upper limit, which is now x. We have seen in the first fundamental theorem of calculus where both the lower and upper limits of integration were both numerical values. So a is actually a constant. It's our lower limit of integration. That will be a numerical value. But x is going to be, in fact, the variable x. We did not want to have the integrand in terms of x just to avoid confusion. So we did change it to a different variable t. So let's say we want to take the integral from a to x. Again, a is just any number of 2t dt. Well, using the first fundamental theorem of calculus, that means we are going to antiderive 2t, which is t squared, and then we are going to evaluate that from x to a. Now, what does this mean? This means that we're evaluating at x, so x squared, and then minus a squared. So what I'm going to do is just simply erase this middle part right here to make it simpler in our proof, and I'll move that equal sign. So essentially what this means is x squared minus a squared. So far, what I have right here is this inside piece inside these brackets, the definite integral from a to x of f of t dt, and I have what it equals. I want to show that if I take the derivative of this, so the derivative with respect to x of this side, I will do that to both sides, I will show that we will get out, in fact, f of x. So let's take the derivative of both sides to see what happens. So I'm showing what it equals. Well, I want to prove, I want this to equal f of x. Let's see if it in fact does. F of x would actually be, since this is f of t, 2t is f of t, f of x would just be 2x. It would be plugging in x for t here. So let's see if we do in fact get out 2x over here. When we take the derivative on this side, the derivative with respect to x of x squared is 2x. Remember that a is just a constant, it was just a numerical value, so the derivative of a squared with respect to x would just be 0. So we do in fact get 2x out. So we did prove that the derivative with respect to x of the integral, definite integral from a to x of 2t dt is in fact 2x. Now that is just showing that I'm just plugging in x up here. This bottom part right here, it doesn't matter what it is. I've showed that when we end up taking the derivative there, it ends up being 0. Let's take a look at another example of the second fundamental theorem of calculus. We want to take the derivative of an integral. Now, our upper limit of integration is x. Our lower limit of integration ends up being 0 here. All that matters is that it is a numerical value. It does not necessarily need to be 0, as we saw previously. It can be any numerical value, a. All we're doing using the second fundamental theorem of calculus is plugging in our upper limit, which happens to just be x. So what this ends up equaling, using that second fundamental theorem of calculus, is I'm plugging in my integrand, the square root of t squared plus 1, but I'm plugging in x because it equals f of x now, not f of t. So it equals the square root of x squared plus 1. Done. That seems very straightforward. It seems kind of strange even. Let's take a look at the next two examples where we won't simply have x up here. We will have something a little more complex than x, and we will in fact need to use the chain rule. As we can see in these next two examples, parts A and B, if we do want to take the derivative of an integral here with our upper limit being something with x in it, no longer just simply x, it will be a little bit more complex but not too crazy. So when we're finding f prime here in part A, what that means is we need to take the derivative. So we need to take the derivative with respect to x because we want to find f prime of x of our integral from pi over 2, a constant, to x cubed of the cosine of t dt. Well, using our second fundamental theorem, what we need to do is simply plug our upper limit here, x cubed, into this function here, cosine of t. So it will end up being the cosine of x cubed. Now, because this is not simply x, it is x cubed, we do need to apply the chain rule next. So we need to take the derivative of x cubed and multiply by that. So that will be 3x squared. And in final answers, when we have a trig function, we do normally write that last. So we can rewrite this answer as 3x squared times the cosine of x cubed. Now this seems a little bit strange. Like, what are we doing here? I think the second fundamental theorem always threw me a little bit for a loop. Like, I feel like I'm just sort of working in a loop, not really accomplishing much. Let's look at this from a more straightforward way using the first fundamental theorem. So I'm going to now re-explain part A in sort of a different way. So I'm going to do that using green over here. So we're not on part B yet. This is just an alternate way to look at part A. So if we take a look and we allow f of x to simply equal the definite integral from pi over 2 to x cubed of the cosine of t dt. I am going to use the first fundamental theorem of calculus to just simply evaluate this. So that means take the antiderivative, plug in x cubed, and then subtract, plugging it in at pi over 2. So the antiderivative of cosine of t is going to be the sine of t. So this is really the sine of t, and we're evaluating it from x cubed down to pi over 2, which means I'm plugging in first the sine of x cubed, then subtracting and plugging in pi over 2. Now remember, the sine of pi over 2, it is 1. If you look at your unit circle, it doesn't necessarily matter what it is. It's a constant is the important part. So our point being, since this is still f of x, our goal, again, was to find f prime, right? So if I want to find f prime, that means I just need to take the derivative. When I take the derivative of this here, when I take the derivative of the sine of x cubed, I get the derivative of sine is cosine, so we get the cosine of x cubed, and then using the chain rule, I have to multiply by the derivative of x cubed, which is 3x squared. Then the derivative of this guy is just 0, goes away since it's a constant. So as you can see, we end up getting the same answer here for f prime. This is just sort of a shortcut way of finding the derivative using the second fundamental theorem. And then I sort of proved it in, I think, a more straightforward way using the first fundamental theorem. The important part here is that when we use the second fundamental theorem of calculus and our upper limit of integration is not simply x, but rather, for example, x cubed or the sine of x, something involving x but not simply just x, we do have to account for that chain rule being used. So in this case, it's still very simple of just plugging in that upper limit involving x into this function here. However, when it's not just x, like here it's x cubed, we do have to multiply by the derivative of that to account for the chain rule. Let's take a look at part B. Once again, we want to find f prime, and f prime means taking the derivative with respect to x of what this equals. So we're taking the derivative with respect to x of the definite integral from 0 to sine x of root t dt. Using the second fundamental theorem, what this equals right here is I'm plugging in my upper limit of integration since it is something with x, and our lower limit of integration is a constant, so we can use that second fundamental theorem. So I'm plugging in sine of x into our function. Then, because it's not just x up here, it is a function of x, we do have to account for the chain rule, so we have to multiply by the derivative of the sine of x. The derivative of the sine of x is the cosine of x, as we just previously saw. And so this is our final answer here for f prime. This next example is one involving a graph. We are told that g of x equals the definite integral from 0 to x of f of t dt, where f is a function whose graph is shown. So here we can clearly see this is the graph of f. And what I'll do is rewrite what g of x equals so we can see it a little bit more clearly. We are defined that g of x is a different function, but it involves f. So g of x equals the definite integral from 0 to x of our graphed function f of t dt. So basically, whatever we plug in for x here to evaluate the function g, whatever we're evaluating g at, we can simply plug into our definite integral. Now we do have to recall that a definite integral between two x values represents the area from under or above the curve up to or down to the x-axis. Now remember, if that area is beneath the x-axis, it is a negative value. So if we take a look at estimating g of 0, let's see what that means. So finding g of 0, we'll do an orange. G of 0, plugging in x, would be the integral, definite integral from 0 to 0 of f of t dt. When our upper and lower limits of integration are the same constant, our area is nothing. It is 0. And that's one of the properties of integration. It also makes sense because we're finding the area from 0 to 0. So we're not moving left or right at all. And so it's area of basically nothing. Our next one is evaluating g of 2. So evaluating g of 2 means by plugging in 2 for x, it's a definite integral from 0 to 2 of our function that's graphed f of t. So the definite integral from 0 to 2 of f of t dt. Let's sketch that. So it's from 0 to 2. So here's x is 0, here's x is 2. It's the area of this region here, which happens to be a triangle. And since it's beneath the x-axis, our output will be a negative number. So let's find the area of this triangle right here. The area of a triangle is 1/2 base times height. The base of this triangle is 2. The height of this triangle is 4, or you can think of it as -4 since it has to be negative anyway. So 1/2 times 2 times 4 is 4. So this output here, this definite integral, because it's beneath the x-axis down to the function, is negative, so -4. The next value we want to find is g of 4. So g of 4 is the definite integral from 0 to 4 of f of t dt. So go ahead and pause the video and see if you can get this one all on your own. So this definite integral has a value of -8, and that is because you can look at this in kind of two different ways. It's essentially twice the area of from 0 to 2, and it's the entire green triangle right here, base of 4 and height of 4 or -4, however you want to look at it. So when we do the area of a triangle, we do get 8. Because it's beneath the x-axis, it is negative. Next, we want to find g of 6, and g of 6 in a similar way represents it's the definite integral from 0 to 6 of f of t dt. Now we are going all the way, so it's all of this down here, which is -8, and then it includes also going all the way out to 6. So it's all of this added together in here. So all of this guy, this is a trapezoid in here, and then all of this triangle as well, which is -8. So we know that it is -8 plus some other value to give a final output. That other value represents this extra from 4 to 6 here. So finding the area of this trapezoid here, we need the height of the trapezoid, and then we need the bases. So the two bases of a trapezoid are the parallel sides. So one of the bases will be 2, the other base will be 1. The height of this trapezoid here is 4. So we'll have 1/2 times the height of the trapezoid. The height of the trapezoid again is 4. The sum of the bases, one of our bases is 2 and the other is 1. So that is 3 for the sum of the bases. So we'll have 1/2 times 4, which is 2, times 3, which is 6. So our trapezoid area is 6, which is positive because it's above the x-axis. So this final output here is -2 when we add them together. Now that just means that this negative area sort of wins out over the positive area. There's more area beneath the x-axis than there is above it from x equals 0 all the way to x is 6. So we keep summing as we go more and more to the right. We're getting the total of positive minus negative values. Go ahead and see if you can get what g of 8 is next. Pause the video and hit play when you think you have it. G of 8 is 4. And you could do this fairly quickly because we do need the total up through 6, and then we can add the integral from 6 to 8. Well, we know that the integral from 0 to 6 of f of t dt is -2. We found that previously. Then if we go from 6 to 8, we have to add that part on. Now this trapezoid right here is symmetrical to this one over here that we did in yellow. It has the same dimensions, and so therefore its area is the same as 6, what we found before, so it's also 6. When we add these two together, the integral from 0 to 6 plus the integral from 6 to 8, we get our total from 0 to 8. So -2 plus 6 is 4.
This will be the last example in our video, and in this case, we want to find f as a capital F as a function of x. Right now, it is sort of a function of t, and we want it to be in terms of x. We can see that our upper limit, as we've seen previously in this video multiple times, is x. And then after doing that, we want to evaluate at different x values. Now, could we simply plug in 0 here, use the first fundamental theorem of calculus to evaluate what that is? Yes, but then we'd also have to then plug in 2. That one would actually be easy, but then plug in 5 and do the same thing. What we can do to sort of eliminate all that extra algebra is to find f as a function of x first, meaning use the first fundamental theorem of calculus to rewrite f of x in terms of x only, rather than in terms of t. So the first thing that we're going to do in blue up here is this. So I'm going to use the first fundamental theorem of calculus to simply take the antiderivative of this, plug in x, then subtract, plug in 2. So our antiderivative here, again, still in terms of t, is going to be 1/4 t to the 4th plus 2t squared over 2, which is just t squared, minus 2t. And then, of course, we want to plug in and evaluate from 2 to x. So we are actually first plugging in x. So when we plug in x, we'll have 1/4 x to the 4th plus x squared minus 2x, and then subtracting, plugging in at 2. When we plug in at 2, we'll have 1/4 times 2 to the 4th. 2 to the 4th is 16. 1/4 of 16 is 4, so that first term is 4. Then we'll have plus 2 squared, so plus 4, then minus 2 times 2, minus 4. So these two terms end up canceling out when we plug in the 2. So we actually only have this minus 4 here, which if we just erase the parentheses, we will be fine since there's no like terms to combine. So we have just successfully done the first part of this problem. We have found f of x in terms of x using the first fundamental theorem of calculus. Now this problem really does not involve the second fundamental theorem. It simply sort of has the look of it. It would involve the second fundamental theorem of calculus if we were asked to find f prime. We're not. We simply are using the first fundamental theorem to evaluate a definite integral. It just so happens that our upper limit is a variable and not a numerical value or a constant. So we end up not getting a numerical value out, but rather something in terms of x. So now the reason that we did that is because it's much easier now to plug in whatever values of x that we want. So the first value of x we want to plug in is 0. When we plug in 0, we will simply just get -4. That one's not too bad. Next, this is an interesting one. We want to plug in 2. Now I do want to point something out. You might be able to see what plugging in 2 will get. If you look at it from this original perspective here, what is the definite integral from 2 to 2 of anything? Well, as we learned previously, properties of definite integrals, if the lower and upper limits of integration are the same value, then the definite integral equals 0. We're essentially evaluating this from 2 to 2, subtracting the same thing from each other. So if we plugged in 2 here, I'm just going to do this extra algebra, I know because I like doing it, and I just want to prove that we will get 0 out. It should work. So if we plug in 2, we'll have 1/4. Oh, we already actually plugged in 2. And what did we find? So we found 1/4 times 2 to the 4th, that was 4. And then we had plus 4, plugging in 2, so we're up to 8. Then we have minus 4, and then minus another 4. So when we plug in 2, we do in fact get 0 out. So it does work. The last thing we want to do is plug in 5. So plugging in 5 will be a little bit more difficult. When we plug in 5, we'll have 1/4 times 5 to the 4th. 5 to the 4th is 625. So we'll have 625 to the 4th. Then we'll have plus 25 then minus 10, and then minus 4 more, so it'll be minus 14. When we simplify this, we'll have 6/25 plus, let's see, 11. 11 is really 44/4 to get a common denominator here. And therefore, our final answer is 669/4. And that is what f of 5 is. So while we're not explicitly using the second fundamental theorem here, because we are not asked to find the derivative, essentially the derivative of an integral, we do have some notation that looks like the second fundamental theorem. We're using the first fundamental theorem to essentially plug in a variable and get our function in terms of the desired variable, our upper limit, which is x. Then, once we have a function, we're essentially using pre-calculus to evaluate at different x values. Now, when plugging in 2, we did use the calculus idea, properties of definite integrals. When the lower and upper limits are the same, then our output is 0. So we can use the second fundamental theorem of calculus along with the first fundamental theorem. They do kind of marry nicely, and as we've seen kind of throughout this video.